Hello and welcome to Chemistry Online. The topic today is crude oil, petroleum. So crude oil and petroleum are one and the same thing. You can tell in many areas of life where crude oil is used day by day. It's in the kitchen, used in cooking, as your gas cookers. The gas used in cooking is a fraction of petroleum, crude oil. Or is it in your transportation system, your cars? They use petrol, which is a fraction of crude oil. Or is it in the surfacing of roads, making roads good enough for cars to drive on? We use bitumen and other residues, which are all fractions of crude oil. In fact, crude oil is the most important source of fuel nowadays. Now, it's also from crude oil that we can get hydrocarbons. The hydrocarbons we did in our organic chemistry. The methane, ethane, propane, and all other hydrocarbons we can ever think of. They are gotten from crude oil. That's petroleum. Now, what is this crude oil? How does it look to some people that have not seen crude oil before? Crude oil is a dark, sticky, viscous liquid. It's dark in color. It's sticky. It sticks. And it's viscous. It's a thick liquid. It's not like your light oils. It's thick. It doesn't flow easily. So it's viscous. And it is found in huge underground deposits in many parts of the world. So it's found underground. So you have to bring it out from underneath the ground, or some are embedded inside the rocks, and some underground inside under the seabed. But wherever they are embedded underneath, they are in large deposits. So Nigeria is one of the countries that is rich in crude oil. So hence the more importance why we should discuss it. Now, natural gas always is usually found together with crude oil. So when you are mining crude oil, you'll be getting along with crude oil some natural gases, maybe which can be useful also. And some are just impurities. Now, how is this crude oil? How was it formed? It's in large deposits underneath the ground. Did it just arrive there? How was it formed? It was formed from remains of marine algae and animals. Dead bodies of animals and algae, that's remains. So when large quantities of these dead bodies settle on seabeds, sea bottoms, they mix up with mud, under the sea bottom. And then as they mix up, as the mud and the other sediments pile on the dead bodies, keep piling on it, it becomes hot. So the intense heat and pressure will keep building until a waxy material that looks like wax is formed. This material is called kerogen. Now, as the heat keeps building, this kerogen will change from waxy nature to liquid and gaseous hydrocarbons. And this process where kerogen is changed into liquid form is called catalgenesis. Alright, so when that liquid is formed, then crude oil is ready in the ground. So it just has to keep forming until it's large enough and ready for mining. So an oil well will produce predominantly crude oil, then with some natural gas is dissolved in it. So how do we bring out this crude oil from an oil well? Do it through exploration first. Exploration, then you drill. Exploration is, searching for rock formations, areas which are oil bearing, that has oil. I mean, areas of the land, areas of the earth, whether it's in rocks, whether it's in the sea or on land. That's exploration, searching for those areas where oil can be found. Now, you do this using photographs from A-plane view, aerial photographs. And then if one rock, if a particular area is found, let's say it's a rock, then this rock is examined. And when it's examined, okay, then you can drill. That's core drilling. And then after you examine the rock surface, you explode a dynamite in deep holes. That you drill a little core on the, not little, deep core on the rocks, and then you put in a dynamite there that can explode. And when it explodes, it will send out shock waves as it cracks the rock. Now, these shock waves can be recorded by geologists. And from their training, they will use those recordings to be able to detect if that area really has oil or not, as if it's an oil-bearing area. So if it's an oil-bearing area, then we have to drill. So crude oil is extracted by drilling. How do you drill? We drill deep holes, or we call it wells, oil well. So you drill in deep holes or wells into the ground. Now you keep drilling, just like you would drill a borehole. You keep drilling until it gets to the area that has the oil, and when it gets to that oil bearing layer, crude oil will start to shoot up into the air through the nozzle of the drill. And when that happens, you can connect pipes and then pump the crude oil into tanks, and then it can be sent to the refinery either by pipelines or by tankers. Now, when it arrives the refinery, we can't just use crude oil the way it is. It's too crude, it's too raw. That means it cannot be used as a fuel because it's too heavy. So we have to break them down and bring out the constituent parts, the different parts, the different fractions of that crude oil, which will then be very useful. So that is done using a fractionating column. That's fractional distillation process is used. So fractional distillation will separate the mixture, that crude oil mixture, into a number of different parts, and we call these different parts fractions. So this is done using a tall fractionating column. This fractionating column is fitted above the mixture, with several condensers coming off at different heights. Now, this fractionating column is hot at the bottom. The bottom has the hottest temperature, about 400 degrees Celsius, and the top of the column is about 40 degrees Celsius. So it's cold, it's reasonably cool up there. Now, so take notes, the hottest temperature inside the fractionating column is 400 degrees Celsius, so it can only heat up that crude oil up to 400 degrees Celsius. So apart from that, whatever it cannot separate out at 400 degrees Celsius will be left behind as residue. So we have 400 degrees Celsius at the bottom and then 40 degrees Celsius at the top. So the crude oil is then put into the fractionating column and heating starts. And substances, the fractions with the higher boiling points, will condense at the bottom because it takes them it takes high temperature to condense, to evaporate, or to boil uh, those fractions, those substances, so they will be condensed at the bottom, because the bottom has a hotter temperature. But those that have low boiling points, those ones that can boil at 20 degrees Celsius, 30 degrees Celsius, they're already with at the top, because the top there, the temperature is 40 degrees Celsius. So just listen to the illustration so that you understand better. Now, since the fractionating column is varies from 40 degrees Celsius to 400 degrees Celsius, and crude oil is put into it. When the crude oil is heating starts, and then the fractions of the crude oil that's maybe boils at 40 degrees Celsius will boil and evaporate, and then it will be collected by condensation into another tank. The ones that can boil at 100 degrees Celsius will boil when the temperature of the fractionating column reaches 100 degrees Celsius, will boil and then evaporates and is collected to another separate tank. So it keeps happening. So the ones that will be boiling at 150 degrees Celsius and 200 degrees Celsius will boil when the temperature reaches that point. So the substances keep separating themselves out as the temperature reaches their boiling point. So as this keeps separating out, you have the different fractions until you have the fractionating column hot as 400 degrees Celsius. It can get hotter. So the ones that can be collected at 400 degrees Celsius, they are collected. The ones that are still left behind, they don't have enough heat, so they will be left behind as residues. So let's see, what are these different fractions that come off at these different temperatures. The first fraction you get is petroleum gas. They are liberated at the top of the column, because they boil at the range of 40, 20, 30, 40 degrees Celsius. So they'll be liberated first. They'll come out first, because once the temperature of the furnace reaches 40, petroleum gas should be able to boil at that point. So it comes out and is condensed and taken, transferred to another tank. So petroleum gas, it consists of 1 to 4 carbon atoms per molecule. I always say, consider carbon atoms as firewood. The more firewood you put in the fire, the more smoke you have, and the more difficult it takes to burn, more time it takes to burn. But if you have less firewood, you just have one, it takes a lower amount of time for it to burn out. So we have the petroleum gas having 1 to 4 carbon atoms per molecule. So they are going to be coming out first. Now, examples of this petroleum gas include methane, ethane, propane, butane, and ethane. So most of your alkanes, and then ethane. They are used mainly as fuels for homes and industries. So your cooking gas falls here. And also they are used for the manufacture of hydrogen, used for the manufacture of carbon sulfide, tetrachloromethane, and for the manufacture of ethane. So petroleum gas comes out first in the fractional distillation of crude oil. Now the second fraction is petroleum ethers, and then the ligroins. They come next after petroleum gases. Now it's a mixture of very volatile liquids that can catch fire easily. They consist of hydrocarbons with 5 to 7 carbon atoms per molecule. So you see the carbon atoms here in the petroleum ethers and the ligroins, they have increased. The ones from the petroleum gases, they are 1 to 4 carbon atoms per molecule. This one is 5 to 7. So you see that the more the carbon atom increases, the more difficult it is for it to ignite, for it to boil faster. So you understand that. So the petroleum ethers and the ligroins, they have 5 to 7 carbon atoms per molecule. So the petroleum ether will boil and then evaporate and is distilled between 2 degrees Celsius and 60 degrees Celsius, while the liquid will distill between 60 degrees Celsius to 100 degrees Celsius. So the second fraction, the petroleum emitters and the liquid need from 40 degrees Celsius to 100 degrees Celsius, while the first one just need about 40 degrees Celsius. So that is for the second fraction. So the first fraction, petroleum gases; the second fraction, petroleum emitters and the liquids. And the third fraction is petrol. Petrol, the one you most know, the one cars use. So petrol, or commonly it's called gasoline. It consists of 4 to 12 carbon atoms per molecule. It is very volatile. It catches fire easily. Don't try to check if it catches fire easily by pouring it on paper and say, let me put fire on it. It catches fire real easily. So that means it's volatile. So it distills over the temperature range of 40 degrees Celsius to 200 degrees Celsius. So when the temperature of the furnace or the fractionating column builds up to 40 to 200 degrees Celsius, petrol should come out at that temperature. And as you may already know, petrol is used as fuel for aeroplanes and motor vehicles, but it's also a good solvent for paints and grease. That means it can dissolve grease easily. So if you rub your hand on grease, you can use petrol and pour it on your hand, and it dissolves easily, and you wash it off. So apart from being used as fuel for aeroplanes and motor vehicles, it can also be used as a good solvent for paints and grease, so oil paints and grease. All right, so that's the third fraction. And the fourth fraction is kerosene. The fourth fraction you get from the fractional distillation of crude oil is kerosene, and this one consists of 12 to 18 carbon atoms per molecule. And the fractionating column has to be heated up to 200 to 250 degrees Celsius, between 200 to 250 degrees Celsius for kerosene to come out. Now, this one is not as volatile, it's not as easy to ignite as the petrol, but it's fairly volatile. So this one is safe for burning. You can use it to burn whatever you want to burn. You pour it and safely put your match on it, and you have a safe fire. So it's used as fuel for lighting and heating. You use it for those that use lantern. They use kerosene. They use the other kerosene lamps, and also for heating, kerosene stove, and any kind of heating. It is also a good solvent for grease and paints, just like the petrol. Now, the fifth fraction is gas oil and the diesel oils. So this one consists of 12 to 25 carbon atoms per molecule, and then it will distill when the temperature of the furnace, of the fractionating column builds up to 250 degrees Celsius to 350 degrees Celsius. That's when diesel oil and the gas oils will come out. And they are used mainly as fuels for heating also, and for diesel engines. But they are also used as raw materials for the cracking process. So you heard that one, cracking process. We're going to discuss cracking as a topic on its own, so you understand. But a quick one, cracking is just converting the less useful fractions of this crude oil to more useful ones. So this point is saying that we can use this diesel oil and convert it to petrol, because the demand for diesel in the world is not as high as that for petrol. So we can convert some of the diesel to petrol by cracking process. So we'll discuss that. Now, the sixth fraction from the fractional distillation of crude oil is the lubricating oils. They are heavy oils. They consist of more than 200 carbon atoms per molecule, and they will distill when the temperature of the column builds up to 350 degrees Celsius to and above. And they are viscous, actually. They are thick liquids used for lubricating moving parts of engines and machines. So actually, lubricating oil can be redistilled. We can further put it into a distillation process again to obtain Vaseline and paraffin wax. I'm sure you know about Vaseline actually, if you don't know about paraffin wax. But Vaseline is used in hair care products, while paraffin wax is used in making candles, making waterproof materials, making polish, making ointments and creams. Paraffin wax. So the seventh and last, so to say, fraction of the fractional distillation of crude oil is the bitumen, and then we classify other residues here. So bitumen and other residues, they are solid residues left behind at temperatures above 400 degrees Celsius. Now, since the fractionating column can heat up to 400 degrees Celsius or 500 degrees Celsius above, up to 500 degrees Celsius, so to say, when it gets to 500 degrees Celsius, the crude oil still left behind that could not distill over, they will not be able to distill anymore because the heat in the column cannot go further. So they will be left behind as residue. So that's the bitumen we're talking about. Bitumen is used for surfacing roads and airfields where airplane lands, while other residues may be used as fuel. It's like you will pack kernel and put in fire. It can be used to serve as firewood. So all these residues can also be used as fuel. They can also be used in protective paints. The residues can also be used in pipe coating, and then can also be used to waterproof roofs, to make roofs waterproof. Water resistant. All right, take note of this. The air around a petroleum refinery is more likely to contain sulfur oxide (SO2), carbon monoxide (CO), and nitrogen oxide (NO2). So those are the impurities. We said that in the drilling of crude oil, some natural gas is also dissolved in it, comes together with it. So these gases, while you are separating the different components in the refinery, the gases also will be liberated to the environment. So these are the impurities that can be found in the area and the air around the petroleum refinery: SO2, CO, and NO2. Okay, so we have discovered the crude oil from the ground. We have explored, and then we have drilled. We brought it to the refinery. We've distilled it, and we brought out the different fractions, and then they are ready for use. Petrol can go to the petrol station, and then you buy and use. But over time, it was discovered that petrol that is brought from the refinery can have some issues. It can lead to knocking off engine. It's not a high quality petrol, so something had to be done. And also it was discovered that the amount of the useful fractions, the petrol, the kerosene, the gases from the refinery was less than the amount of the less useful ones. Take for instance, if I get 10 liters of crude oil, so to say, I'm just using this illustration, and then when I get to the refinery, after distillation, I find that I have 2 liters of the useful fuels. That's the petrol, kerosene, the gases, all make up 2 liters. And then the 3 liters is the diesel, the bitumen, and the oils, which are less useful to humans than the petrol, because the petrol, the kerosene, and the gases, they have higher demand than the diesel and the oils and all those in the environment or in the world. They have higher demand. So if I'm supplying that kind of low rate, so the demand will be more than the supply. So what can be done? So we have to convert some of these less useful fractions of crude oil to more useful ones. And I told you the other time, that can be done by cracking of petroleum. So, crude oil is a mixture of hydrocarbons with different carbon chain lengths. Like we said, we're saying this one has 4 to 12. We had said the other one has 1 to 4 carbon atoms per molecule. The other one, that petroleum emitters have 5 to 7 carbon atoms per molecule. Petrol has 4 to 12 carbon atoms per molecule. Kerosene has 12 to 18 carbon atoms per molecule. From this 5 to 7, even from 12, you already have long chains of hydrocarbons. So repeated units of carbon, the chain of carbon is too much. It's becoming a long chain hydrocarbon. So some hydrocarbons have a lower boiling point. The short chain hydrocarbon, the small hydrocarbons, the short chain hydrocarbons, like the 1 to 4 carbon atoms per molecule, all those ones, they have low boiling points. That's why they are more volatile. So that means they are more easy to ignite. That means they are more useful as fuels. But how about those larger hydrocarbons? That's the one that have from 5 to 80 carbon atoms per molecule. They have a higher boiling point, so they are harder to ignite. That makes them less useful as fuels. So after fractional distillation, we find that we have a large supply of the long chain hydrocarbons, larger supply of the long chain molecules. And this means that the larger proportion of the less useful fuels are produced. So we have more proportion of the less useful long chain molecules produced from fractional distillation, and which makes the demand for the more useful ones more than the supply. We cannot supply enough because the demand is daily. It's a day-by-day demand for petrol, for cars, gases, for home use, day by day. And if the supply is so low, and we keep supplying the less useful ones in abundance, you see, the demand is more than the supply. So to solve this problem, the long chain hydrocarbons must be broken down. They must be cracked into smaller, more useful molecules. And this is the process we call cracking. So cracking of petroleum. Cracking is a process by which a heavier hydrocarbon molecule is splitted into 2 or more lighter hydrocarbon molecules. So you split a heavier hydrocarbon molecule, like when we say the hydrocarbon molecule that has 13 carbon atoms is heavy. So C13 will have H28. So let's say that's an alkane, C13H28. By cracking, we want to break it down to smaller, lighter hydrocarbon molecules. So we want to have molecules that are not as big as C13. We want to break down the C and the H actually. So if we break down that, we can break down C13H28 to C8H18 and C5H10. So at least the C8 and the C5, they are lighter than the original alkane that was C13. So that's a cracking process, breaking down of higher hydrocarbons to lighter hydrocarbon molecules which are more useful as fuels. And this will allow the supply of short chain hydrocarbons, that's the useful hydrocarbons, the fuels, to meet the demand for them. So that is that. Now we have different types of cracking. You have the thermal cracking and the catalytic cracking, 2 types. Now thermal cracking is the use of high temperature and high pressure for cracking. So here the less volatile crude oil fraction, let's say the kerosene, is less volatile than petrol. So let's convert kerosene to petrol. Let's crack kerosene. So we pass this kerosene through a chamber. Then we heat it to a very high temperature, say 1000 degrees Celsius, and very high pressure, 70 atmosphere. Now this kerosene is a long chain alkane, will be converted into smaller chain alkanes. So by converting it, you will have alkanes, you have alkenes also, depending on how it's broken down. So let's say we had C12H26, since kerosene has 12 to 18 carbon atoms per molecule. So we use C12H26. If C12H26 is cracked, is passed into cracking process, can be broken down in different ways. Can break down C12 to C8 and C4. 4 plus 8, C makes 12, but at least C8 and C4, they are lighter than C12 itself. So C12H26 can be broken down to C8H18 plus C4H8. That's still the same thing, but it's broken down to lighter versions. It can also be broken down in different ways. C10 and then C2, that still makes up 12. Or C4, C5, and C3. So it can be broken down in different ways as long as it is broken down to lighter hydrocarbons. But the issue with thermal cracking is that, you don't have a control of what you will get. So you can't say, okay, I'm cracking this kerosene, I want to get a hydrocarbon with just C4 and then C8. That's what I want to get. You cannot decide that in thermal cracking. It breaks it out the way it comes out. You see, the way you see it, you take it, but actually to break it down. So you cannot control the cracking pattern to yield your desired chain length. So that's why thermal cracking is not commonly used in industry. So that will lead us to the second type of cracking, catalytic cracking. Now this one uses low temperature and low pressure, and then uses a catalyst. So you put in your large hydrocarbon and heat them to around 500 degrees Celsius, and you pass it over a zeolite catalyst. Zeolite catalyst is finely divided silica alumina. So this catalyst will break the bonds in the large hydrocarbons and will make the molecules of between 5 to 10 carbon in chain lengths, which are more useful in petrol. Okay, so catalytic cracking is better, because firstly, you can control the cracking pattern. So it's more controllable, that you can adjust the process so that you have a desirable product of certain chain lengths. And then secondly, the process will not only yield more petrol, cracking process will yield more petrol since you're converting maybe kerosene or oils to petrol. It yields more petrol now than it was from the fractional distillation. Not only that it will yield more petrol, but also it will give petrol of higher quality than the one obtained directly from petroleum or petrol fraction during the distillation of crude oil. So remember I told you that petrol from the fractional distillation of crude oil may still have some issues and not so much good qualities. But if you pass it through catalytic cracking, the petrol produced there has a better quality. So catalytic cracking gives you more yield of petrol, and number two, gives you a better quality of petrol. Okay, so there is something we call catalytic reforming. So reforming is another process of improving petrol quality apart from catalytic cracking. Reforming involves making structural changes in the presence of a catalyst to a hydrocarbon to improve its anti-knock activities, trying to improve its qualities so that it won't result to knocking of engines when used in motor cars. So actually how it happens is like isomerism. In isomerism, you are not actually breaking down, you are just rearranging the molecule, so it will still have the same molecular structure but different pattern that you're just rearranging. So reforming is like that. Reforming is, maybe you had C12H26, you can just arrange it. You had a C8 still petrol fraction because you want to just get a better quality petrol. You're not cracking actually. So you already have a petrol fraction C4, let's say C4, or maybe C8. but you want to rearrange it to have a better quality, you can rearrange it to, through reforming. So take notes the difference between reforming and cracking. Cracking is the breaking down of larger hydrocarbons to smaller or lighter hydrocarbons, while reforming does not do breaking down. Reforming is rearrangement of the hydrocarbon molecule to give a better yield, to improve the anti-knock activity. So reforming is an isomerism process. Now, while cracking an alkane hydrocarbon, the product formed can be an alkane and an alkene. So we have to deal with tests for alkenes. I know we've done this before while we did organic chemistry, but let's look at it again. Alkenes are more reactive than alkanes. So we test for alkenes using bromine water. So bromine water is orange in color. This is just a reminder because we've done it before. So if we put in an alkane into bromine water, which is orange in color, and we shake it, we shake the mixture together, the bromine water should turn colorless. If that happens, then that substance you put in there to shake is an alkene. So if you are given an equation in exams that a substance, or you're given a substance and you're given bromine water, say, put in the substance A into the mixture, the bromine water, and then shake vigorously, however you're asked to shake. Then observe if the bromine water turns colorless. You may be asked, what is the inference? So the inference is that that substance was an alkene. Hope you understand that. All right. So we're talking about anti-knock activities of an engine, and that can be determined using octane rating. So we're going to consider octane number. So the quality of a fuel is indicated by its octane rating. So this octane rating is a measure of its ability, the fuel's ability to burn in a combustion engine without knocking, without pinging. So knocking is the same thing as pinging. So combustion engine is any engine that uses petrol to ignite, uses fuel to ignite. So your car is a combustion engine, your generator is a combustion engine, your motorcycle is a combustion engine. So the quality of fuel, petrol you use can be bad, and if it's a poor quality, it can lead to knocking of the engine. Knocking of engine makes the engine go bad and die easily, die fast. So where you buy your fuel can affect your engine. So it's not just to maintain the engine. Also, buying a good fuel is another way of maintaining your engine. Now, a straight chain alkane like heptane, remember heptane has 7 carbon atoms, heptane. So a straight chain alkane like a heptane is assigned an octane number of 0. So heptane has octane number of 0, while 2,2,4-trimethylpentane, which is a highly branched octane, so 2,2,4-trimethylpentane has octane number of 100. So that's the standard. So if you have 100 and 0, you can put in your fuel, and see where your own falls. So you see where it should fall for you to have a safe or good quality fuel. Petrol containing a higher percentage of the straight chain hydrocarbons, that's the heptane. Petrol containing a higher percentage of this straight chain hydrocarbon will cause more knocking than the one that contains a higher percentage of the branch chain hydrocarbons, that's the 2,2,4-trimethyl. So you need more of the 2,2,4-trimethyl than the straight chain pentanes or heptanes. That means your petrol is a mixture of branch chain hydrocarbon and straight chain hydrocarbons. But all we are saying is that if the straight chain hydrocarbons in the petrol is more than the branch chain hydrocarbons, you are going to have a bad quality petrol, which can cause knocking of the engine. But if you have more of the branch chain hydrocarbon, then you have a better quality petrol. So the quality of any petrol is rated according to its octane number. This octane number is the percentage of heptane to the percentage of the 2,2,4-trimethylpentane. So you remember, it's a ratio. How much pentane compared to the how much heptane compared to the 2,2,4-trimethylpentane are in that petrol mixture. Alright, so that's what we call octane rating. Now, your cars, the taxis, your cars and motorcycle, your generators are petrol engines. They use petrol. And that's because petrol is the only fuel that meets all the requirements necessary to power a motor car engine. So we call motor car engines petrol engine. Now, a motor car engine has a number of cylinders. Now, usually it's 4 cylinders. And they are fitted with pistons. The pistons will keep moving up and down as the engine is working. Now, when the engine is working, the pistons move up and down inside the cylinder. Each upward and downward movement of a piston is known as a stroke. And a motor car engine works on a 4-stroke energy cycle. So it should go up and come down, and then you have a 4 times. So you have a 4-stroke energy cycle. That means at each cycle, there must be a correct ignition of the fuel-air mixture. What I'm saying is, the fuel to air mixture should be ignited at each cycle to provide energy. So when it completes one cycle, at that point it completes one cycle, the fuel and air mixture should ignite. If that happens before it completes the for the cycle, then you have a problem. The engine will knock. But if it happens after the cycle is completed, then you're going to have air pollution, black smokes coming out of the exhaust. So let's see how this works. Now, for efficient working of the motor car engine, the fuel air mixture must ignite at the correct stage in each cycle, and it must be completely burnt. So at the correct stage, not before the cycle is complete, and then must be completely burnt. That is, not after the cycle is complete, because if the cycle is complete before the fuel air mixture is ignited, then it will not be completely burnt, and that will lead to air pollution. So the fuel should possess the correct volatility and should possess the correct temperature of ignition for it to be burnt at the right time of the cycle. So if the fuel is too volatile, if it's too volatile, it will have too low an ignition point. So if it's too volatile, if it catches fire too fast, that is, it will ignite before the cycle is complete, and each cycle is complete. That is too volatile. Then if the fuel is too volatile, it will be burnt prematurely, as it will ignite before the cycle is complete. When this happens, a condition called knocking or pinging will result. So knocking will reduce the efficiency of the engine and it will shorten its lifespan. Now, on the other hand, if a fuel which is not volatile enough is used, that means it has a high ignition temperature, it may not be burnt completely. So it will result in air pollution, as you have excessive black smoke and unburnt hydrocarbons expelled from the car exhaust. So in the burning of petrol in an internal combustion engine, normally fuel is ignited at the spark plug. The spark plug. So the combustion will spread after the ignition. It will ignite at the spark plug and then spread uniformly outwards. So ignites and then spreads. That's how it should go. So petrol with an octane rating that is too low for the engine can ignite prematurely, ignite before the cycle is complete, ignite before it even reaches the spark plug. So it does not ignite at the spark plug, the point there, the tip there. So that's a premature ignition, and that will result in uneven burning. So it will not burn uniformly outwards, and that will cause knocking of the engine, pinging of the engine. So It means knocking is caused by premature combustion. Say it again. Knocking is caused by premature combustion. Okay, so as a summary, I would say that cracking is a process where higher chain length hydrocarbons are broken down to smaller and more useful hydrocarbons, and then by so doing it will yield more engine fuels and also will give better product petrol. And also that reforming is another method of producing better quality petrols. So reforming is the process by which atoms are rearranged into different molecular structure in the petroleum industry. And I also say that the impurities that are likely to be found in the air around a petroleum refinery are SO2, sulfur oxide, CO, carbon monoxide, and NO2, nitrogen oxide. And there is a term called petroleum glut, GLUT. That means oversupply of petroleum. And then we also talked about alkenes, how we test for alkene. That alkenes decolorizes bromine water. That's it changes bromine water from orange color to colorless. But then you may have a question that comes like this. On cracking medicinal paraffin, a gas is evolved which gives a pop sound with a lighted splinter, and an oily liquid which decolorizes bromine solution is also obtained. What are the products of this cracking? So you are asked and you are given, they explain the characteristics of these gases, and you are asked to identify those gases. That's what it means. And the first description was that a gas is evolved which gives a pop sound with a lighted splinter. If you didn't know, that's a characteristic of hydrogen gas. Hydrogen gas will ignite fire, make fire burn brighter with a pop sound. Just pop sound. That's so. The first description there is hydrogen gas. So hydrogen gas burns with a pop sound with a lighted splinter. And the next description was an oily liquid which decolorizes bromine water, bromine solution. That is an easy one, That's a characteristic of alkene, since alkene decolorizes bromine solution. So that means the products of the cracking are hydrogen gas and an alkene. Hydrogen gas and an alkene. So I hope you understand what we just learned under petroleum. If you have questions, arrange them and ask your questions. Other than that, have a nice day.